we're talking today. This is the proposal. There's no guarantees on this yet for the Mach 2 hydrogen hub. This was put together by some local politicians, some local, I call it marketing or public relation firms, and these are good. These proposals are coming in all over the country, and Corey will talk a little bit about that later. But the Department of Energy is putting some major dollars out there to fund potentially quite a few hydrogen hubs around the United States. The Philadelphia area called the Mid-Atlantic, and MACH stands for Mid-Atlantic Clean Hydrogen Hub. So just on the record, ISA Philadelphia has no affiliation with this. It's just something that's out there in the public domain. And obviously, you know, being in the Philadelphia area, we would welcome this and hope that something like this would land. But proposals like this are all over the country. So if you'd like to learn more, I'll put the link in the chat here. And maybe, is there anybody on the call that is involved in this project or would like to chat about it or volunteer something? Okay, we'll move on then. So just briefly, I'll share with you this link. If you're part of the if you're in the ISA Philadelphia section now, welcome. If you're a guest, welcome. If you're an ISA member, you can join any geographic section you'd like. The Philadelphia section is an active section in good standing. We do programs like this at least 3 times a year, probably more this year, including a couple local tours that we have planned. But we would welcome your membership in the ISA Philadelphia section. I'm joined today by Fred DePasquale and Sue DiPaolo. Together, we're part of the volunteer board. Fred is our secretary and Sue is our treasurer. So we welcome you here today on behalf of ISA Philadelphia. But with that, I'll introduce our guest speaker. Corey Marcon is a friend, and he's been with ISA Philadelphia before. Corey, I'll stop sharing my screen if you want to take over. He's the energy business manager with Endress & Hauser. That's his full-time day job, so to speak, but he does volunteer for things like this to talk to ISA. So we welcome him here today, and thank you, Corey. This presentation will be recorded. If you have any issues with recording, you are free to leave, but you know, we appreciate if you could hang around, and we'll listen to what Corey has to say. Corey, how would you like us to handle Q&A? Do you want him to put them in the chat? Do you want him just to open up the mics, or what works best for you?
It's a small group, so I don't mind an interruption and a dialogue. I'm always happy to clarify or discuss further as we go along, or if there's anything in the chat by the end, happy to wait and respond then.
Sounds good. So feel free, play it by ear. If you got something, chime in, put it in the chat, and we'll work it in. I think everybody's mic is allowed. If you want to, if you do want to mute it while Corey's talking, feel free to do that. Otherwise, open it up, ask away. And thank you for being here today. Corey, I'll turn it over to you, sir.
Yeah, thanks, Jeff. As you kind of alluded to, my day job is with Endress & Hauser, instrumentation company. Specifically, I cover power and energy as an industry manager. So it's technically a marketing role where, you know, as much as it's about communicating a message, it's also about learning and communicating what the market needs are back to our own organization to get more voice of customer in our innovation process. But for today, you know, the title, as you saw, it was Safety in the Details. I've really been kind of beating the drum with this mantra. I think hydrogen is having yet another moment. Probably, you know, some that are much older than me would say it's like the 3rd renaissance. You know, we also say nuclear is on its 5th renaissance. But there's something different about this moment where you have new technologies scaling like electrolyzers. And Fred, you even mentioned the biomass to hydrogen pathway, where there just seems to be a bit of new life in this molecule, specifically on the production side, knowing that there's also emerging end uses as well. So I've been talking about safety in the details because everything's very focused on the high level. You know, we've got the Inflation Reduction Act, we've got the Infrastructure Investment and Jobs Act, and the hydrogen hubs, and there's just a lot of money. There's a lot of projects being announced. There's a lot of startups coming into this, and instrumentation is very much the details of these types of chemical plants that will, you know, be 300 megawatts of electrolyzers, for example, on our grids around the country. And you know, pressure transmitter, okay, maybe it's $1,000, maybe it's $2,000, but there's a million different configurations in that device. So we really are talking about the nitty-gritty details of a project when you consider that those are fundamental in the safe operation of that project. So we'll kind of discuss some of the permeations of hydrogen across industry, where, you know, Anderson Hauser sees it intersecting with various decarbonization goals, but also, you know, other legitimate use cases for chemical in refinery industries. Then we'll kind of get a little bit of a refresh on functional safety, and then talk a bit more about some emerging applications. And that'll basically be the meat of the presentation. So it's kind of been hailed as this Swiss Army knife of decarbonization. Certainly hydrogen is not new. Refineries and chemical industries use it to the tune of about 10 million tons a year in the US, about 90 to 95 million tons a year in the world. And 95% of that production is this gray hydrogen, or, you know, coal gasification, or even more popular, steam methane reforming. So that's natural gas or hydrocarbon feedstocks to then produce, you know, hydrogen for an end user that's often very close by, right? It's like you have your SMR plant at your chemical plant, or your SMR plant at your refinery. And it's used as a catalyst. It's used in ethylene crackers, all these various applications, and that's hydrogen that, you know, when it's produced using a fossil fuel, you're venting carbon monoxide, carbon dioxide into the atmosphere. So right off the bat, you know, there's the decarbonization of those sectors, and that's, you know, I don't know how much you guys know of the colors of hydrogen, but if you throw carbon capture on a fossil-based feedstock, it's blue hydrogen, right? If you're talking about electrolysis, even if you're talking about grid-tied electrolysis, which, you know, sometimes the grid's running on coal, especially at night, then you typically will call that green hydrogen. I think an important thing to note is that we're, you know, as an industry, moving away from the colors. You know, I still think they're useful for training our sales force, but the policies are all going to be written around carbon intensity. So Fred mentioned the project where it's, you know, hydrogen from biomass, and it's probably like tree clippings or things that they were going to kind of trash regardless, that, you know, may increase the health of the main tree itself. And, you know, there are scenarios where if you use that type of feedstock, you're actually, you know, carbon negative. So that's kind of greener than green if we really think about what the colors are meant from a metaphorical standpoint. So again, I think the colors are useful, but certainly everything's all about the carbon intensity now. You know, personally, Anderson Hauser, we don't have a horse in this race. We want to support all industries. You know, we think that all of them have a place. I will say with steam methane reforming, and we could talk about this later when we're into the application details, lower pressure applications. You know, hydrogen's coming out of the inlet of your pressure stream swing absorber, you know, maybe 150 psi, slightly elevated temperatures, let's say like 100 to 120 F. So you're not necessarily dealing with the same risk profile that you are with other emerging production techniques of electrolyzers or high temp electrolyzers or hydrogen from biomass gasification and other organic waste. So to take a step back, safety, instrumentation, automation, fundamental, right, to the safe operation of a plant. For us, we participate in different initiatives. The Center for Hydrogen Safety is a group run by the American Chemical Engineers Society. Fantastic group. I can't highly recommend this enough. They will go through actual like incidents, like real life, like O2, NH2 failed, caused like a tank to rupture, and they'll do like root cause analysis. They reach out to the operator of the of whatever the asset was that failed. They collect all this information. They present it back to a group of functional safety engineers that just ask questions, and with the goal of safety by community, right? At that point, it's not a bunch of hydrogen companies trying to compete with each other. It's a bunch of engineers working on hydrogen that have the common interest of safety across every hydrogen application, right? To avoid that kind of Hindenburg effect of a former time, right? We want to make sure that we don't have a major safety issue, or God forbid we do. It's well understood. I love to give the example actually of the Plug Power image of the flaring that was happening at a gas station that was caught on somebody's cell phone, and people freaking out and putting it on the internet. And actually that was a pressure relief valve working perfectly fine. And so the safe release of hydrogen into the atmosphere through that flaring process was actually the everything was operating correctly. We're also committed to doing some smaller intimate technical forums to make sure, again, we get more voice of customer into our innovation process, and then of course our participation in ISA or other working groups. And by the way, open to having this conversation with other ISA groups, but also your feedback on what you guys are doing to stay kind of in the know of all things hydrogen. So safety in the community, those are the different layers. Thinking about emergency response, how is it communicated to the broader community? Down to mitigation, prevention, controls and monitoring process, right? In mitigation, we start to get into that world of SIS, and then really the heart of it for instrumentation automation is in that BPCS, down and very close to the process. So as far as a safety instrumented system versus base process control system, these can be separate. They seem to have converged over the years with certain kind of like DCS vendors. We are totally agnostic in terms of what that network looks like. But I will give the anecdotal story of an electrolyzer company that kind of ran into some cybersecurity concerns around not really separating the SIS from the BPCS, like physically, right? Separate panels, dedicated IO to what is a fault that will trip and cause a major shutdown, to prevent a catastrophic failure, versus what you're monitoring, versus what you may be using to ramp up and down the operation of the plant itself. And when you think of an SIS in its proper form, it comes down to three elements. The sensor is, let's say, your lead. It is your vote, Your logic solver is, the math in the middle, where you set your thresholds on things like, an overpressure event or a level, over, a high alarm for level, and then your final element. Maybe it's a pressure release valve, maybe it's a drain valve, maybe it's, um, a pump kicking off, or maybe a pump kicking on. It could be a bunch of different things, but it's really the combination of those three elements that create the subsystem of that SIL loop. So when you're evaluating instrumentation vendors, and you're considering reliability, I kind of say there's two types. There's the inherent reliability, so that's just working with suppliers that follow, best in class quality standards, things like ISO 9001, or even calibration standards like ISO 17025, and then the SIL level of the device itself, which has a lot of rigor around electronic failure. And I will dial a little further into that message in terms of the, let's say, limitations of what SIL really is relative to application risk in subsequent slides. And then there's proven reliability. Kind of consider this the ongoing plan to ensure reliability in that leading vote, right? That instrument that's telling you what to do in the case of an issue. And there are ways to do onboard verifications and partial and full proof testing in these instruments, not just ours, right? That's the trend that we're seeing across instrumentation manufacturers, that I think it's wise for folks to consider that because it can make safety easier over time, right? It can make it much more simple for your operators to prove out, safety over time.
Hey, Corey, this is Jeff. If I may ask, I mean, in your general opinion, or maybe you've heard this question before, is a SIL rated instrument, SIL 2, SIL 3, whatever, generally regarded as better than a non-SIL rated instrument in terms of quality and performance and reliability?
Yeah, so SIL is somewhat of a paperwork exercise. For us, it's like a very nominal cost adder. So, in my opinion, I would just throw SIL on everything. If it's in a safety system or not, and then you just have that paperwork available. It's like, $20 maybe on some instruments, some we don't even charge. But it is an important exercise. So once a vendor has gone through the work of getting a product SIL certified, effectively what they've done is dissected every single component inside of that electrical assembly that, we in the end of the day call pressure transmitter or flow meter, right? There's a lot more than just the Wheatstone bridge or the Coriolis tube. There's all the sensors that interact in order to kind of have that physical principle relate all the way to a 4 to 20 output or some other, Profinet or whatever comes out to go back to the system. So I would say working with manufacturers that have SIL in their portfolio mean you're in a different class of manufacturer. But I wouldn't say necessarily that each instrument, whether we throw SIL on it or not, it's pretty much the same instrument. But, SIL comes with the paperwork needed if you're ever audited on your system.
Appreciate it, Corey. Thank you.
Yeah, no problem. Yeah, so this is just kind of showing the life cycle. We start to get involved in the design and engineering as you start to consider, certain SIL instruments, right? Kind of as Jeff alluded to, at some point when you're speccing out safety loops, you do have to consider SIL. Sometimes you don't. Sometimes you can get around it with other things like, redundancy There are a lot of like specialty transducers out there that you may not have SIL on ever. And so you just do, you add 3 instead of 1, those types of calculations, because overall what matters is the safety loop becomes a bit of math homework for your engineers. And so the SIL instruments make that math homework easier, because it's like we've solved our own math problem and we're giving you our information to feed into the overall math problem. But certainly you can achieve an SIS, like a SIL loop without SIL rated instruments. And then the installation, commissioning, ongoing operation and maintenance. That is kind of what I was discussing with respect to how do you operationalize safety over time? How do you proof test something? So there's really 2 types of failures as it relates to SIL. Again, I want to draw that like very clear circle, that this is the world of electronics that we're talking about. We're not talking about an instrument in hydrogen yet. We're talking about an instrument as it exists that would, potentially fail just because of the electronics. And so there's the burn-in and wear out, where you just have a higher risk, just because, if there is a fault in the factory and it does get out, you would typically see that soon. And then at the end, that's how you kind of determine the overall expectancy, is just things start to get a little bit more, the chances increase that something's going to fail at the end of its life. And then in the middle is just where, it's just a random failure rate. So now what I'm going to kind of move into is the application risk, right? So if I was talking about SIS and I was talking about electronics, now I'm talking about maybe some mechanical risks associated with, in this case, the hydrogen itself. And I'll go through quickly 3 applications here. So, you guys probably know the basic periodic table. Hydrogen's small, and because it's so small, it's leaky. We have a lot of infrastructure set up for natural gas and even methane leaks. I think I saw somebody from Sensodyne on the call, and I think a good thing to mention is that hydrogen, because it's a diatomic, it can't really be seen with infrared. And so a lot of the newer higher end gas detection actually can't see hydrogen. So flame detection, fine. You can see the hydrogen flame with like a UV IR type of sensor, but with the gas detection, the top of the line, what's out there snooping, methane facilities, you hear about like the drones flying overhead and seeing big plumes of methane. That's not possible with hydrogen. First of all, because of the measurement principle in those drones using mostly infrared. And second of all, because hydrogen dissipates so quickly, you don't see that same kind of like pluming effect. It's hard to compress. So the thermal conductivity is really the coefficient there that ends up driving the difficulty to compress. I'm not a thermodynamics guy, but maybe some of you are. The reverse Joule-Thomson effect is very strange. It does affect us as a gas analyzer provider. I thought I saw Honeywell on the call too, so you guys probably understand this as well. It's like when you're dropping pressure for an analyzer, it's actually heating instead of cooling, whereas other gases would experience a like a cooling effect when you're expanding. That's why in LNG you use turbo expanders, and hydrogen you use compressors to do liquefaction. Is this notion of the reverse Joule-Thomson effect? So just something to keep in mind when you're designing interconnect piping to gas analyzers. Permeation and brittlement. This is not just in pressure transmitters, what I'll talk about, but also just in any sort of steel. And it's faster rates in different steels. And there's a really good, somewhat recent ASME standard, B31.12, that dives into this with quite some detail. And I will tell you, ChatGPT has read ASME B31.12, so you can ask it, hey, show me the part of the code where different metals are on the the no-fly zone for hydrogen, and it'll help you navigate what is otherwise a 400-page document. So um, just a little millennial wisdom for you there. And then the combustion complexity, and I'll discuss this a little bit when we talk about the hydrogen blending.
Did ChatGPT write your presentation, Corey?
No, it didn't.
Okay, you had me worried there for a minute. All right, as long as you reference it, that I think we're okay.
Yeah, it hallucinates a little too much to rely on. But yeah, so I'll just quickly go through three applications that we see emerging or at least changing in this new hydrogen renaissance. First is the permeation through pressure transmitter membranes. This is a pretty well-known, well-understood phenomenon. I mean, we're talking about already having 100 million tons of hydrogen in the world in production today at various facilities. And these facilities do use gold-plated pressure transmitters because it's very well understood that high pressure, high temperature, what I mean by that is, really anything over 100 psi, anything over 100 F. That's kind of the real easy rule of thumb. You want to start looking into a gold-plated membrane. And we have a pretty good manufacturer declaration that talks about this. And it talks about it in terms of partial pressure, which partial pressure matters when you're considering blends of hydrogen. So if you had a plant that was or like a natural gas facility or natural gas end user that was blending in hydrogen, you can use the partial pressure rule to determine, well, does a 30% blend at this pressure, this temperature, you'd calculate that to a partial pressure of hydrogen. Does that warrant this kind of additional cost for this additional safety? And really, the important thing to understand is that this is a creep. This is not like a fast fail type of phenomenon. You'll get pitting. The hydrogen will permeate around the membrane, and it'll sit in the fill fluid behind the actual diaphragm of the pressure transmitter, and it will therefore cause a drift. And you may see it over time as you start to understand your process, but you'll be replacing pressure transmitters that aren't working, and that's obviously not good for particularly for safety applications where it really matters. So for us, we kind of released a new pressure transmitter product line this past year, and in doing so, reading the tea leaves on hydrogen, we decided to do some additional testing to determine what our standard gold-plated membrane should be that we apply. We get it electro-polished onto our diaphragms, and you can kind of probably intellectually understand the phenomena and the trade-offs there, or the conundrum, I should say, right? Like the more gold you put, the thicker the membrane, the less sensitive it is to the change in pressure. Now, granted, gold is soft, so it's not a huge impact. And then there's also ways that you can do the manufacturing process, like do a compensation on temperature and pressure after you've electropolished the membrane, which can really honestly significantly minimize any sort of let's say risk to the performance based on a thicker membrane. But we looked at 5, 10, and 25 micron, and at 5 and 10 we saw some pitting, meaning like, well, what's the point? Like if you are creating, or if you're spending some extra money and an extra step in your manufacturing process to add a layer of gold, um, you know, why add a layer when you may end up actually having pitting, and therefore kind of a false sense of security. We see that as like a probability risk, like it's all like a probability risk. Like we saw that, um, I can't say the exact numbers, but we saw a certain amount of pitting in 5 that was less than 10 that was non-existent in 25. So we decided to land on 25 microns without any sort of significant trade-off to the overall performance. And we've actually had customers, major oil and gas customers, ones that have had hydrogen experience for the last decade at their refineries, mandate 40 microns. So just to give you kind of a flavor for that challenge across different manufacturers. So this is a big issue. And as I mentioned, the SMRs, the steam methane reformers, pretty consistent application. Now we've got a bunch of different hydrogen applications at different pressures, different temperatures, and that increase in pressure, that increase in temperature does increase the permeation rate of these membranes. And gold significantly slows, but it's mostly, let's say, impermeable to the hydrogen, so that you'll get a lot more longevity out of your pressure transmitters, and you won't get that short-term drift on an annual basis. So I did kind of touch on this. It's partial pressure, temperature, and exposure time. So if you were, let's say, doing the Long Ridge Energy project, which I'll allude to in a later slide, they were blending hydrogen for a demonstration, and so that's temporary. We weren't telling them, hey, every single pressure transmitter in your gas fuel system needs to go hydrogen, because that's just not realistic, given what the application is. So this isn't to press a panic button or to scare you guys. This is just to let you know that the tools exist for a more robust system. But honestly, it's dependent on the application, which is evolving based on large scale demonstrations, it being temporary versus full scale new applications with higher pressures, higher temperatures, for example. So that's actually a picture of me with Mark Berry from Long Ridge Energy. And we provided some technology there that I can touch on in a subsequent slide. But hydrogen blending is in and of itself a pretty complicated topic. There are different end users. You can basically categorize it into 2 buckets. One is pipelines. The others are fuel systems. And when I say fuel systems, you could further subcategorize that into gas turbines, like the one that you see in the background there, gas, large ones or small ones like aero derivative, peaker units. You could see boilers blending hydrogen, reciprocating engines, which Wärtsilä just finished a blending demonstration in, I think it was Illinois. So everyone's kind of racing to determine, hey, can I blend hydrogen to reduce my carbon footprint? And if the answer is yes, then what is my downstream risk, and how much does it cost to mitigate that risk? And so if I just double tap on fuel systems, where personally we've had the most experience, and where I do think that the let's say the risk is a different profile than pipelines. Fuel systems, think of them as like a short amount of pipe that's going to an end use. A boiler, engine, turbine, and there's different issues around what that means for operators. Of course, there's practical things like hydrogen may have by mass, a higher heating value by volume. It's about a third of methane. It's more flammable. It's also more it has a higher flame speed, which can cause some issues in the actual combustion process. So we see dry low NOx gas turbines actually publish limitations that would, effectively trip the whole turbine, because you would melt the fuel nozzle, the hottest part of the flame, which has been so engineered for methane. It will kind of that new geometry of the flame, by introducing 30, 40, 50% hydrogen, would actually move the hottest point of that flame to the fuel nozzle itself, causing it to melt. You got to trip your turbine, you're down. That's hundreds of thousands of dollars a day, and fuel nozzles aren't cheap. Pipelines, a little bit more about materials. It's less of an issue in terms of time, because their end user could be miles away. So any sort of blending is probably more about knowing that your hydrogen is sufficiently blended, more than it is about knowing the percent hydrogen because of like an operational issue that you have to deal with in real time as a turbine operator, for example. So I just kind of copy pasted from ASME B31.12 some of those different alloys that are kind of on that no-fly zone. Those same materials obviously would apply to the fuel system as well. I just decided to put it here, as the pipelines seem to be a little bit more concerned with their existing infrastructure. It's a much bigger problem for them to solve. So in a scenario where you need a fast compositional measurement to prevent that overshoot, right, going from 25% to 35% can actually mean the difference between melting a nozzle and not melting a nozzle. And flow meters, the other control valves that are in the system, they can fail, or they can have an issue, or make a bad reading. And so we've seen this emerging need for some sort of validation. And it can be done with a chromatograph. It can be done with other, like a chromatograph with a thermal conductivity detector. There are other ways to measure it, but Raman spectroscopy kind of offers this faster response. We're talking about 30 seconds. Plus, it can just be pretty much put directly into the pipe, and it's an optical measurement, so you don't need to flare an altered sample. You can just take the sample at process pressure, return it to the pipe in which it came. So really emission free, allowing for that continuous measurement. And that's the technology that we provided along with our flow meters for the Long Ridge Energy Project, the last Earth Day, that was able to demonstrate the hydrogen blend on the large combined cycle power plant. So moving on to finish up here, I'll go a little faster, just I want to leave some room for some conversation, is purity. Purity is another emerging application that I think is, I venture to say, like, fundamentally misunderstood, because, I see specs and they say hydrogen analyzer, and they're just completely made up. They're like, all right, we need a hydrogen analyzer to make sure that something is 99.999% pure. And it's like, you're never going to get that. Like, there's no technology on the market that is directly measuring hydrogen and then calculating, yep, it's this pure. Really, and that's what this little blurb says from the DOE, is it's about determining the maximum level of contaminants. It's about looking at the contaminants and then back calculating the purity. And the reason why I bring this up in a safety application, or a safety presentation, is really because there can be some downsides to impure impure hydrogen, making it out into, for example, the mobility market. I mean, you can have significant corrosion on a fuel cell to the point of complete failure. And so, this is more about considering how we need safety across the whole value chain, right? When you deliver hydrogen, it needs to be pure for the safe operation of whatever is being used, or whatever the hydrogen is being used for downstream. And I make the controversial statement, unlearn J2719 and ISO 14687, just to say that this is all about the end use of hydrogen. And this has historically been written around every single possible location the hydrogen could come from, whether it was an electrolyzer, or whether it was coming from coal gasification, or maybe it was a byproduct of a chloralkalizer for chlorine, production, and then of course the SMR pathways. And if you had to measure all of these different contaminants at the end use, you're starting to get to a place where it's just economically unfeasible to do so. And so ISO 19880, especially table 8, and this is virtually what you see from this is what I want to show you, is that, like, if you just think about impurities based on the feedstock and the plant operation by the hydrogen production technique, that's when you start to get towards a more cost-effective way to ensure that downstream safety once you're putting hydrogen into the open market, is to measure purity at the source, because purity by the different techniques of production is a much easier challenge to solve than a catch-all analyzer that doesn't exist at the point of end use. And that's really the point that I want to make. For example, with electrolyzers, your feedstock's water, and your purge gas is typically just nitrogen. And so what that means is, as far as your process goes, your only two contaminants are oxygen that went the wrong way, right? When you split the H2O into H2 and O2, O2 goes, let's say, left, and oxygen goes right. That cross-membrane permeation, as it's called, or moisture that's kind of, in a vapor state, evaded all of the various steps of separation and drying for the purification of hydrogen downstream of an electrolyzer, right? Those are your two, primary process-related risks. Oxygen and hydrogen, and then your purge gas is a risk associated with your maintenance. It's associated with a restart. And so what we see in this case is, like an electrolyzer plant, like green hydrogen facility, would shut down, purge nitrogen to vent out any residual hydrogen, and then when they restart, they would basically do a procedure called produce to vent, where they're then taking hydrogen, producing enough volume of hydrogen to push out the trapped purge gas within all the piping between the electrolyzer and the vent. And so, effectively, if you're able to monitor the trace H2O and O2, you can kind of get that online hydrogen purity, because as soon as you move from producing to vent to, actually closing the vent and producing to compress or store or whatever you're doing downstream, your only two risks are moisture and oxygen. And so that's a much easier challenge to have, analyzers. You can see, some that we've provided for electrolyzer companies that are measuring trace moisture, trace oxygen. And so that was really it. I just wanted to kind of touch on those topics. I think hydrogen purity is evolving, and really has to do with the safety across the value chain, right? Making sure downstream consumers of hydrogen that's produced are ensuring safe operation. hydrogen blending is a phenomena that is growing in interest and also understanding. And there are a lot of challenges there around, stratification of the blend over long periods of pipe, so you can have big bursts of hydrogen. You know, when it comes back to an end user, unless you're remixing hydrogen, there's various technologies to ensure that you've, correctly blended that hydrogen so that you don't have those issues. And then, of course, the permeation of the pressure transmitters being something that we've always kind of understood, but now has a little bit more to contend with in terms of the types of applications that you would see in a world where hydrogen's not just produced by, steam methane reforming. So thanks for your attention, Jeff. Thanks for the opportunity. Happy to take some questions.
Thank you, Corey. Yeah, so there are a couple things in the chat here. If you want to comment on those regarding the sill-rated transmitters, and feel free to open up your mics and talk to Corey. It's an exciting time. It's something we've had around forever. I mean, most process plants have some type of hydrogen applications, especially refineries, power plants. But it's exciting to me that we're talking for the first time in a long time about wide-scale adoption. Kind of like Corey said, the Swiss Army knife. I don't know if it solves all problems, but it sure it checks a lot of boxes. I'll give it that. Any questions for Corey?
Corey, I just wanted to ask you a little bit more about you were mentioning that ASME spec as far as metal. I know you said it's a huge document. Does it go through basically what alloys you could, is it mostly specialty alloys? Did it talk about carbon steel? Does it talk about your typical grades, or is it that they recommend, especially for vessels and on it? And I'm thinking mostly on my standpoint of batch reactors. I know because a lot of solvents have recently become outlawed or restricted. A lot of fine organics or small molecule pharmaceutical plants depend on hydrogen for their synthesis, and it's become a critical raw material for a lot of those plants. So my question is, I just wondering if you could give us a quick synopsis about what it goes through and all.
Yeah, totally. So it's kind of two parts. It's industrial piping and pipelines. And so there are two sections of the standard, and I believe they each have their own, let's say, no fly list / approved materials. Just to simplify the words, and it's stainless steel is great, like dual rated 316, 316L, 904, no problem. It's actually when you get into like titanium and Hastelloy, and even super duplex, where you start to see more permeation risk. So it's actually it's interesting for us when we do a high pressure Coriolis, and there's our competitor that there's basically two of us that can do very large Coriolis, right?
Yes.
And there's we use super duplex to achieve high pressure, large line size. They use Hastelloy. And neither works for hydrogen. It's great for carbon capture, no problem. Dense phase CO2 flows right through it, not an issue. But what that means is that as you scale up electrolysis, for example, you get these mega plants with a huge amount of hydrogen rolling through it. Like you could theoretically see a scenario where you just have to split your line into multiple flow meters in order to get to a high pressure line size where there is a stainless steel high pressure solution. Because if you just say, I want a Coriolis and I want a Coriolis that's real big, then you may run into some issues. I personally, I don't know what's going on in biotech in terms of the types of materials that they use, but I do know that stainless steel is very, very common, but there's also the single-use stuff that I know even less about, where those are probably legitimate concerns to look further into.
It's interesting what you mentioned, because I know that I personally have done batch hydrogenations, and the base vessel on the batch was Hastelloy C276. So I know, it's an it, because remember, you're talking about it's a solid, you're using different solvents, you're using usually a palladium on carbon catalyst, something like that, so you've got this kind of aggregate multi-phase product within, that you're starting with to hydrogenate. And it's for the batch side, and the amount of hydrogen they're probably talking about, you're not talking major embrittlement, but from all the safety bells and whistles that you talked about, absolutely know exactly what's going on there. But that's great. Thank you.
It's a question, Fred. Thanks, Corey. Well, while we're waiting, if there's anybody else, for those who may have joined, I'll throw this up on screen. Corey, if you give me just a second, I'll steal the show. If you joined us late and you're interested in learning more about ISA, I'll put the ISA Philadelphia Connect site in the links. If you're an ISA member, we appreciate it. If you're a member of ISA Philadelphia, we appreciate that as well. One of the things I learned about ISA is you can, maybe it changed during COVID, I'm not sure, but you could live in Timbuktu and belong to the ISA Philadelphia section. You no longer have to live within a geography, maybe you never did, to be a part of the local section. So if you like our section, we